Today we're gonna talk about two different topics, a shorter one, a longer one, and both are gonna involve the memory in some capacity and a lot of sketching, probably. As for the first one, we're gonna talk about the garbage collector. Or, well, more the memory management in C# in general. And it's not gonna be a long one because you don't really need to know too much about that, which is why I personally don't know too much about that, and the garbage collection is actually... I'm not gonna say it's difficult, but there's a lot to know and understand about garbage collection, which is why a lot of these things that we're gonna talk about now are the interfaces that we as regular mortal programmers are allowed to see. And they're designed to handle all the complicated stuff in the background, and we should just trust the engineers who make the frameworks to do their job right. So first of all, why garbage collection in the first place? We had that topic before, and let's start with the basics. Our program is roughly separated into two larger sections in memory. At least the memory that we are allowed to use is split into two parts. We have the stack and the heap. Stack and heap. And usually the heap is a bit larger than the stack. Now, whenever we call a method, let's start, we have the main method here and say static A. We call A from here, and then maybe we have, yeah, autocomplete can sometimes be annoying actually. And then it does something like this where it's just, okay, yeah, cool. Anyway, whenever we call a method, the system will know exactly how much space this method will need. It will know because of compilation that we're gonna have one integer variable here and maybe a reference to a string that's stored safely somewhere else in memory that we don't get to access. And same with B. So B might have integer array. New int 10. Like so, which isn't exactly 10 integers, but just a reference to the array which is stored on the heap. So the main method, we know exactly how many variables we have, how much space we need. We only have this string array, so we know this is about as much memory as the main needs. And then we call the method A, which has an integer and a string. It's gonna need a bit more space. So we call the method, add it to the stack. This is now the memory space for A. And A is gonna call B. And when we call B, we have to reserve another bit of space for an integer. Like that. And you don't see anything at all. I forgot. Sorry. So we have the main method, which takes a bit of space, which then calls A, which needs a bit of more space, and which then calls B, which needs a bit of space as well. The point is, every method itself is mostly located on the stack, because we know exactly ahead of time how much space each method is gonna need. Because we compile the code, we know exactly how many variables are gonna be used throughout the lifetime of that method. Or at least we know the maximum. In theory, the method might return before we actually get to use those variables. So we never actually use the full amount reserved here, but we know how much we are gonna reserve or how much we are gonna need at most, and that's what we reserve. And when the method call returns, we can just free that memory and go back to the caller. So B goes back to A. Once A is complete, we go back to A, main, and we free all that space as well. Pretty straightforward. It's very easy to keep track of where memory is stored and where it isn't. We have always the part up here, which is filled, and the part below, which is free to be used for any method call for our program. very easy, very convenient. Only it limits us in terms of capacity, because we do want things like this, which might actually dynamically reserve space for a certain amount of integers. And that's why we have the heap. When I say I have an integer array, I reserve space for the address in our method b, but the actual array is gonna be put somewhere in the heap. So let's make this somewhat pretty. So let's restore. Actually, let's go back a few steps. Looks better. So B might reserve space for A, which is down here maybe. And this is gonna be like 10 integers, and B just stores the pointer, the address of this part in the heap. So this is the strong boundary, stack, heap, and this is just somewhere in the heap. It's not at the very beginning, though it probably should be, but it can be anywhere in theory in the heap, and we just have the address to refer to it. And here's why we have memory management at all. Once I return from the method B and I clear this stack, let's put this line back in, no one is pointing to our array anymore. Like, this arrow doesn't exist. We don't have any program code, any active code that maintains the address to this array. So once we return from B, this is just dead memory. No one can use it anymore because it's in use already, but nobody knows where it exactly is to recycle the memory space. And languages like C, you have to do that yourself. As a programmer would have to ensure that this space that we reserved is freed again. That is your duty as the programmer, and if you mess up, that's where we get memory leaks. For languages like C#, we have this concept of garbage collection, which means there's an automated process in the background that keeps track of every time you reserve space in the heap. Doesn't matter how much memory you reserve, if it's half of the heap or just one single boolean, in theory, it will keep track of that. Well, sort of keep track of that. It will just know that we reserve space in here, and it will check our stack for any references to that part of the heap. And it will not only check the stack, because let's say I have class C, and we have a field here, public. Let's put the array in here. Well, let's be lazy. Just one element, but it's still an array. And instead of storing that, we're gonna store C like that. So this would be more the case of, let's go back to the drawing board. So method B would have a reference to this C down here. And this C is gonna have a reference to our integer array. Well, actually it should be a bit smaller now because only one element, but whatever. So the garbage collection has to first check our stack, which references exist, which addresses to the heap are in use. And it won't find the integer directly in here, but it will see that this C is in use. And it will see that C itself is then using this integer array. So the garbage collector has to constantly keep track of which addresses in the heap are in use, either directly from the stack or indirectly through one or multiple objects. And you can imagine that going through all the addresses and all the objects takes a bit of time. So garbage collection is a bit more optimized, so it's not constantly checking everything. It has several ways to optimize the process of what addresses do I need to check, where do I need to check. If it finds some memory in here and it has no idea where it might belong to, then it might need to check its own tables. Do I have a reference somewhere? Do I have I seen a memory address somewhere in here, or maybe somewhere else in this whole tree of going from the stack to a reference, to a reference, to a reference, to a reference that points to this integer array? And if so, well, that's in use. And if it's not in use anywhere at all, only then can we free this memory. And there are things like first generation, second generation, third generation garbage collection, where it organizes different references in groups, mostly based on how old they are. So it knows this is a very fresh reference, and I might need to check if it's already deleted. If it's an already pretty old reference, if it's been active for, I don't know, an hour already, I'm not really sure what these cycles are, probably just some seconds or maybe minutes at most. But that's garbage collector internals. I'm not even gonna attempt to figure that out. But generally the idea is the longer the object exists, the more likely it is that it is still in use, and so we don't need to check that now, we can wait till later. But if it's just a very fresh object, there's a good chance that it's also gonna be removed very quickly. Because sometimes you're just gonna have to reserve space for objects to do some processing and just remove all the objects right away. Don't care about them anymore. But yeah, generally, garbage collection in that case is this wonderfully complex thing that makes our job easier as the programmer. At least the programmer on the end product, not for the programmer that has to implement the garbage collection. And it does add some processing fees. As in, it has to go through the memory, which takes time because memory access does actually take time. And it has to do all the processing for all the code that the garbage collection itself runs on. And does a lot of things. And if it's not too busy, in between checking all the references and cleaning all the memory, it might actually refactor the entire heap. So we do actually move, for example, the C up here, clear it out in here, and then maybe we also move the entire array up here. So this part down here is free. With the intention of making later memory access a bit more comfortable by having just larger chunks of memory that are available for use instead of the smaller segments in between. And that's why garbage collection is important. And there are certain interfaces we have that can interact with the garbage collection more or less directly, where you can trigger it to do some heavier processing at a certain moment to free memory. And that's mostly just for us to help the garbage collection figure out when the best time for certain actions might be. Because you as a programmer, you might not be able to help the garbage collection directly by freeing the memory, but you can give it hints about this might take a bit longer, but I have some free time right now where nothing is really in demand, so you can clear now. Or maybe just as a hint that I'm gonna need a lot of memory later, so better free and clean up everything now, so the process doesn't run into issues later on. Because the garbage collection itself, it can only make estimates about, do I run now? What do I do now? What's the best course of action? It's very generalized in that sense. And you might be able to give some hints to optimize it for your program. But we're not going to talk about that because generally it's not the best idea. At least that's as far as I learned it. I have one case where I forcefully call the garbage collection to do some stuff early. And the only reason I do that is because otherwise our program would run into massive memory issues. So we actually have to pause our program and instruct the garbage collection to work now, so it can clean up the memory, so we don't run into out of memory issues. It's not the best code. What are you gonna do? Old code bases. But actually it's not just old code bases, it's just the whole architecture. Getting distracted. But more than these direct interfaces to the garbage collection, we can put little hints on these objects in the heap that give the garbage collection something more to work with, or that help the entire memory management process. And this interface that is directly used for those kinds of things is called IDisposable. And we can add it as a normal interface, whoop, like that, to any class or struct or record or whatever you work with. And the only thing it forces us to add is an method called dispose. We look at the description: performs application-defined tasks associated with freeing, releasing, or resetting unmanaged resources. Ignore the warning down here. We're not going to talk about that yet. Or not at all today, actually. But this dispose is directly intended for freeing up your memory, sort of. The whole concept is you have a method that is intended to be called when you don't need your object anymore. So when this C isn't used anymore, when we don't care about it anymore, we can just call c.dispose to call code that frees up all the related resources with our object C, with this specific instance of C. And quite often that is actually just referring to an internal variable that might itself be disposable. Private C, let's do something like this. C, hold. Wait. Let's make a bigger one. I can type today. Well, it's not like I can type ever. Child. That maybe, and this is new C, and this is C2 equals new C. So what we can do, actually let's just move this out. Is use this dispose and then internally child.dispose. Looks a bit weird, I know, because we're calling ourselves in our own dispose, but just go with it for a moment. I know that this object C is going to take a lot of memory in a more complex way. And so I make it IDisposable to have a direct method of cleaning up all that memory and all the resources that might be attached to it. It's not necessarily just for memory that we call this dispose. It also has other, well, resources, as the name suggests, which might be just you having a lock on a network, for example. Like your program currently grabs all the incoming traffic through the network. And you want to make sure that once we stop using this object, it will also free the lock on the network so that the traffic might be redirected to somewhere else. Or, well, in terms of locks, probably more like a lock on a file. So while we open this C, we might have a lock on a specific file on your hard disk. So no one else can change it anyway, or maybe even read it. And we want to make sure that as soon as we don't need this object anymore, we also free that lock, so some other process might access that file. Or it could be something like access to your screen, if you're drawing something. You might want to make sure that as soon as you don't need this instance anymore, some other part of your process can take over and gets exclusive access to your screen to draw something else on there. So dispose isn't limited to just memory management, but memory is a big part of it. And so what you would do in this case, well, you would make sure that whatever your class does internally, which is not pure C# standard, like I just have a couple of variables in a field, and instead have some other complex structure that itself is heavily involved in system resources, I make sure that I dispose that. And I do that as part of my dispose. So we cascade the dispose down to the lowest level. When I call the dispose on my C, it doesn't need to do anything itself, but it internally holds references to another object that is marked as disposable, which means it itself has complex relationships with system resources. So I make sure that dispose is called. Because if I don't call it, well, no one else has that reference, so no one else will be able to call that dispose. I'm the only one that knows it, presumably. Of course, that's not always the case, but we assume worst case scenario, I'm the only one that knows this reference, that knows about this specific address in the heap. So if anyone can call the dispose, it's me. So I make sure to call the dispose for my data in my own dispose. And someone else can call dispose on me when they get closed. In fact, the standard clearing up the stack will actually do that. Not only that, but one example, once I remove my B from the stack, once the method returns, and all the memory up here is removed, this reference to C is lost. And so later during the cleanup from the garbage collector, it will see that our C is marked as IDisposable. It's inheriting that interface, and that's special to the garbage collection. So it will actually call the dispose method on its own. You might think, if it's already calling the dispose method, why should I bother calling it myself? What's the point of that? And the answer is, in some cases there is no point. It's perfectly fine to not call the dispose, but that's for special cases. Quite often you want to make sure that as soon as you don't need the access anymore, that dispose is called. Because everything else might cause side effects or just massive delays in your program. And you don't want that to happen. You don't want to cause any weird behavior that you cannot track down, because once you lose the reference to your object, you lose any way of checking what the status of it is. So the garbage collection might trigger immediately and call the dispose and clean up everything, or it might call it in 10 minutes from now, while you work on some completely other part in your program. And suddenly you have weird side effects because you think that other part of your program is causing an issue, but the issue is actually caused by the disposing of your original object, which only now occurs, because only now the garbage collection has time to take care of that. So if you don't call the dispose method, directly yourself, you will leave it up to chance when it will be called and if it's going to be called correctly. And that's never a good idea. Just so you know, in theory, you can leave it out and it's not going to be the end of the world. It will cause you a lot of frustration though, most likely, at some point. And there are special cases where you can leave the dispose out entirely because it's not needed. And those cases are where usually you have a parent class that is marked as IDisposable, because most of the child classes that inherit from that parent class do have important changes that need to occur in the dispose method. But that specific child that you're using might not have those resource-intensive changes internally, and so it doesn't need to do anything in its dispose where it's just empty. And in those cases, of course, it doesn't matter if you call it or not. So you can absolutely leave it to the garbage collection. It is better though if you always ensure that dispose is called whenever you don't need your variable anymore. Now, disposing can be done with just directly calling the method dispose. That's fine. But you also want to do that if something went wrong. So maybe I'm some code in here that suddenly has an exception. Or maybe you just want to have an early return lazy. In those cases, this method aborts its progress at that point and never goes to the dispose call down here. Not a good idea. As mentioned, we want to always make sure the dispose is called. If we leave early, we don't have the reference to C2 anymore and we cannot call the dispose anymore. So we have to do it in here. And that's why in those cases, you create a construct like this with a finally. We use a try. No, that's. We use a try, and instead of a catch right here, we simply use a try finally. So this code runs, and no matter what happens, if we return early, if there's an exception, anything, we still execute this code block before finally leaving the method in total. Now this issue is because C2 might not be initialized. If this code itself causes an exception already, then we never get a C2 to work with, so this would not be filled. So I need to fill in something in the beginning, in this case null. That means I might call null.dispose, which is not valid, null reference exception. We talked about those before. So if C2 not equals null, this would be one way to do it. In newer versions, I would prefer to do it this way. Is not null, that's special syntax. But there's a simpler one that you can also use in older versions of C#. I think that was introduced maybe in C#6. Definitely in C#7. It wasn't in 5. But we can add the question mark right before this dot operator. Okay, my dot operator, as always, we have something on the left, and with the dot, we refer to do something specific to that data type. So in this case, call a method in C. And before we add that dot operator, we can add question mark to change the meaning of this dot operator. It's now not a simple call this method on this object type of this specific instance of the object type, but check first if it's null. And if this is null, then you do not continue with the dot operator. We just pretend like nothing happened. And if it's not null, only then do you proceed with the normal dot operator and call the method. So question mark dot is an easy way to make sure that this will always correctly work regardless of C2 being null or not. If it's null, because this crashed, nothing happens, and that's good because we don't need to dispose. If this code worked and only down here it had to abort for some reason, then this code is called correctly and we dispose. So If you have something that is IDisposable, it's marked as IDisposable. You want to make sure that dispose is called at some point, and that's either gonna be a try finally combination, usually, but there's also a simplified way to do it, because writing this out every single time you have a disposable, it's a bit meh. So much work, and it's so easy to just not bother. So there's a different structure where we can take this code like that, and we put this in brackets like that, and add this as a code block, as if this was an if statement, right? Or a loop or anything else, where we have a keyword, and then in these brackets, normal brackets, we put our declaration and initialization of the type we want to dispose later on. Put one too much. What did I forget? Nothing. That. And to mark it for usage in IDisposable, we have this keyword, using. The same using we see up here. This is just another usage for using. Using variable equals something. Well, that just means internally the code translates this into a try finally. Basically. This is just a shorter version for that. No matter what happens inside here, once the code leaves this scope because of a normal return, because the code is finished, or because of an exception, no matter what, as soon as you leave this scope, it will call the dispose method on that variable. That's why using is very convenient, and it's probably the best way to handle IDisposable in most circumstances. There are special cases where the using is inconvenient, and in those cases you fall back to just a try finally. But yeah, that's a using statement, using, and in the brackets you just have the declaration for your variable and set it to some value, and then inside the scope, the code block, you can do something. And just like with if or loops and whatnot, you can leave this code block out if you just have a one-liner. So one line of code, put directly after that. For several lines of code, you want to use the curly brackets to mark this as a larger code block. But otherwise, it's the same basic logic you already know, just for dispose. And going a step further, for the more current version of C#, beyond 7.3, which is a big landmark version. 7.3 is the last .NET Framework version, so if you're working with .NET or Mono or anything, you can use the newer feature. If you're stuck in .NET Framework, this is where you'll stop. But for the newer versions, I would return this. I would just have the variable declaration and the initialization, like this, and put the using in front without any brackets. Like that. And this is equivalent to using this scope to mark the point where we call the dispose. So before I use the using statement and then have a code block after that, and once we leave that code block, we call dispose. And with this newer using statement, again only after the C# 7.3 change, I'm not sure in which version it came. It was pretty early, maybe 8 or 9. Anyway, with this new system, we use the code block or the scope in which you define this using statement. So in this case, only once we leave the method B. Also, this is going to be important. To make something simple. 2, like that. I have a using statement for variable c and one for c2. I first initialize c and then initialize c2. The order in which these are getting disposed once we leave this scope is the same order in which we added them. So we first dispose c and then we dispose c2. If you do not want that to happen, if you want to first dispose c2 and then c, so if you want to reverse the order, then you have to use the older style, the code block. So I would do this using statement, and inside that using statement, I would use the other using, and then I have my code in here. And now when I leave this scope, C2 is disposed, and then I leave that scope and C is disposed. So this is one way to do it. And just using the other way. The important part is it's a different order in which the dispose is called. And that does make a difference if those variables are intersected, if they know each other. So for example, if C has a reference to, or if C2 has a reference to C, then C2 might already dispose C. So there's no reason to call dispose on this one at all. And I can't reach out. Why can I not? There. There are special cases where you have disposables that know each other and store references to one another, and they might perform disposing internally. Or it might be a case of, even if they don't dispose each other, they still know each other. So let's say I have a dispose with which is empty. If I just dispose C first and then C2 at the end of the method, there might be something inside C2 that still uses C. Does that make sense? So we have the older one, the first one, C, which is used by the second one, C2. And once we dispose this one, well, we told the system we do not care about C anymore. You can free all the resources and it's unusable now. That's a consequence of calling IDisposable methods. If you call dispose, you told the system you don't care about it anymore. It can be invalidated. It doesn't need to work anymore, we're cleaning up. But in theory, the reference to C is still there, even if once you call dispose. It's still there, the code is still there, the reference internally and the fields are still there. You just did some things to it that make it not usable, usually. So if you still have a reference to it in some other instance, like C2 right here, and you try to use it because you don't know that it was disposed on the outside, you're gonna run into exceptions sooner or later. So in cases like this, you want to make sure that C2 is disposed first, and only then do you dispose C itself. So as long as C2 is active, C is active. And once you dispose C2, once you don't use it anymore, it's shut down, only then do you invalidate C as well. So in cases like that, where different objects know each other, it's important that you keep track of the order in which you dispose them. And that's when you have to maybe use a different syntax. For the most part, you don't really have to think about dispose too much, because you yourself are unlikely to write anything that needs disposing. Though it is useful in a lot of cases where you don't really use it the way it's intended, but it's just too convenient not to use it. And we get to those cases sooner or later. Just know there's a lot of potential for abuse for this interface, and that's totally fine. It just Usually you yourself don't actually have something critical that needs to be disposed, but you might store other objects, things that need to be disposed. So you only add a dispose method to make sure that your fields are getting disposed. That's the use case you will run in the most. You store something that's IDisposable, so you yourself become IDisposable, so you can dispose your internal values. And whoever is going to store an instance of your type will do the same. So IDispose is one of those things that just trickle up. If anyone further down in the chain is disposable, the very top is probably also disposable. And once you call dispose on the very top, that trickles back down to the very bottom to the thing that actually needs disposing. And that wasn't a short segment at all. I'm not sure if it's clear what it is. Just keeping that in mind. If you store something in a class that is marked as IDisposable, make your class IDisposable as well, and call the dispose of your field or fields properties in your dispose method. That's step one. And if you use code with anything that is IDisposable, make sure you call dispose, either in a finally block of a try finally, or just by using the using keyword in the new style or the old style. Doesn't matter which, just do one of the two. So much for using. Let's get to something a lot more interesting. Just let me get a grip sip. That was half the cup, and I'm out of coffee. Let's go back to the very beginnings. Let's cut this off. Different topic, we don't care about that anymore. Let's think about the basics about how the computer operates. So if you remember, this looks not good, but let's leave it. We had one large segment with memory, with individual memory cells, which contains values in them. And you had a bunch of registers, like the program counter, which store specific data for the computer to operate. And for example, the program counter will keep track of where in your memory we are currently at, so we know where in our program we are. The computer always just executes the code at the position of the program counter. Now, this is one large memory line or sequence. And we only have one program counter pointing at one specific point in this very long sequence. Imagine the following. I have a special register, another special register, and I take the value from our program counter and I copy that over into this special register, and then I change the value of the program counter to somewhere else. Maybe 1000. Way to the right. On this graph here at least. And then I continue executing my code. And then sometime later, I remove this value. Actually, let's keep that in here. And bring the old value back up. And then continue executing. At which point, we run this code again. And maybe advance the program counter, move forward, do some stuff. And then we decide, no, pause, don't execute anymore, copy the value over, store it in this special register, and then put some other value back in here, and then continue executing. And we again continue code far on the right. Until we pause again and restore the older version of our program counter and continue back here. That concept is what is used in older versions of your computer. Actually, it's still used in current computers as well, but especially in the first computers, to allow for multiple programs to be executed at the same time. We now have multiple processors running in our computers. That's the norm. Especially for a modern PC, you will have at least 2 or 4 cores by now, at least current versions. If you still have an older computer, it might have a single core, and there are of course low power computers, specialty users, microcontrollers, where you only have that one core, one computer basically, one electronic unit on the internal side that can do all the processing through our memory, the way we learned a computer works. And that means we could only run one program, which for specialty cases, sure, microcontroller, there's only one thing it should do, who cares? But a PC, where you want to run different programs at the same time, because you want to have your browser open to watch a Twitch video on the side, well, I don't know, reading up on the latest trends in C# development, or probably game something. And then probably in the background you have some messaging app for chatting, or maybe even voice calls. All of those different programs are written by different people and have to be stored in your memory at different locations. They don't overlap. And you want them to all run at the same time, with one core. Doesn't work. The only way you can make that work is by splitting the attention of your one single computer core between the different parts of your memory. You have to execute from one part of your memory, and then interrupt at that point, go to somewhere else in memory, and continue execution from that part on. And then interrupt again and continue from your original part. So you switch between different parts of your memory, which refers to different processes, different programs running. And all you have to do in between is keep track of the special registers. You keep the memory intact as it is, and you just have to swap the content of all your registers. But here it's only the program counter, easy enough. If you have a couple of other registers, you have some more stuff to keep track of and to store, but as long as you keep a copy of your context of the current state of your registers and special settings you need to do, you can always return your program to exactly where you left off. Put it on ice, pull up some other register values, continue from somewhere else in memory, and go back to the first one, then to the next one. And you always give some time to any programmer in there. Because that happens so fast, you as a human don't notice it. Because it can switch between these different parts in memory many times each second. It might only spend a few nanoseconds, maybe a few milliseconds on each program before it continues with another program. Because computers are very fast, it can do a lot in those couple milliseconds it might have time. And that's how you get the original multithreading. A thread would refer to one piece of context. You have one program running around, just very linear. I'm executing piece by piece. Maybe I jump back and forth, sure, but it's very linear. I always know where to go next. But I have another program which is entirely unrelated to that, which has its own segments it might jump back and forth to, which does not interfere with our original one. And I can have a different set of register values which belong to that context of running the program, to that specific program. It's one thread, it's one line of execution that goes back and forth, it's just one line. Same here, it's just one continuous line of program flow. each one with its own context that you have to swap in between, but otherwise you can just easily go back and forth and the program just works fine, regardless of if you abandon it for a few minutes or not. I mean, of course, if it's some real-time application, you as a user will notice because it's not doing anything anymore, but the values will still be valid. The execution still works just as well as it does if you completely focus all your resources on just this one thread. On modern computers, of course, you have multiple cores, so you can actually have multiple of these different threads be processed at the same time. Different cores can focus on different parts of your memory and run truly multiple programs at the same time, truly work multi-threaded. Multiple threads running at the exact same time in parallel. That's possible today, though even in those cases your CPUs have special features for each core to allow an easy switch between different contexts, to switch between different threads. And beyond just the hardware, we have the same in software, where technically the CPU just sees, okay, we have this one process running around in our code here that our computer CPU is running, and only one thread that we focus on one context. But by rearranging the code in between, the order in which we jump around, we can still cause a sort of separate program flow that to the CPU itself looks like one thread, but it's actually multiple different threads. And we're not gonna focus on how exactly that works internally, though operating systems are a really cool project actually. But anyway, multithreading, there's special hardware that is designed specifically for handling multiple threads, and of course the whole problem of organizing different cores that all want to access different memory regions or maybe the same memory region. But we focus on multithreading inside your software, which not necessarily means that your computer is running multiple threads or even multiple cores are running. It might be the case, but it's not necessarily the case. Going back to our program code. When we start our program, we always start in our main method with one singular thread. We have one continuous flow of code that starts in here. This is our starting point. There's only one starting point. But then we can have two different methods. Let's go back for A and B. A and B. And maybe I want to run those not after one another, but in parallel. Maybe I want to run both of these at the same time. And that means I need to have a different thread, a different context for each of them, so the computer can actually run them at the same time. If we don't split the context, if we don't instruct the computer that these two are run in different ways, it will just try to run the first and then move on to the code for the next. And the fundamental tool we have for that in C# is the class thread. And how complex multithreading is depends entirely on how complex you want to make it, because the fundamental system is stupidly easy. I'm gonna start by just creating a new thread, and I'm gonna give it A. Now, this is gonna look a bit weird. This is a new concept. Right now, this is a method group. We pass it on. Thread can have different arguments we pass onto it. So we can use IntelliSense to quickly look at it. We have these things parameterized thread start and normal just thread start with a maximum stack size. Let's not talk about the stack size for now. Actually, let's not talk about it at all because it doesn't matter to you. You're not gonna optimize that. Unlikely, at least. C# has a... How do I phrase this? so far, whenever we passed on arguments, we just have int a as an argument, and I would call method a with the integer value, like that. And inside here, I have now a variable a, which I can output, for example. Sometimes it's incredibly useful to us as a programmer to not pass a variable, but a method. And I don't want to use the data that is provided. I want to use the instructions that are provided. I want to execute them, to run those instructions. And for that context, we have this thing called delegates. I think the concept is basically function pointers, just more wrapped. At least I think that's what function pointers should be in C or C#. We create a variable that doesn't contain an address to somewhere in the heap where data is stored. We provide an address to program code, so to speak. Keep in mind, if we look in the actual memory, your code and your data all look the same. That's all just numbers in the memory. It doesn't matter if it's actually intended as data or as instructions for the computer to execute. It's all just numbers in memory. And so, of course, our program that we write is going to be compiled into just numbers in memory. It's just, usually you don't get access to that. That's protected area. But we still can use the addresses in there to pass around methods in the form of delegates. And there are some different ways we can do that. In the most basic form, we would use a special class called, for example, action. Why did I lose that? Okay, action A. Action is, well, I say class. You can think of it a bit like a class. It behaves like an instance of something, but it's a delegate. You can see it marked here. Delegate is actually a special keyword. You can create delegates. And right now, A expects a delegate that returns a void, so it doesn't return anything, and doesn't receive any data. So a method like this, we have a void, doesn't return anything, and it doesn't get anything. That's the fundamental delegate we can pass on. And so we can just use B, but instead of calling B, instead of putting brackets in here, I just put in B like that. And the computer will understand, at least in this context, that this B is meant as a delegate for this method. It still knows B refers to this method, but we don't call it, we don't execute it here. We pass it on as an argument to another method. So we use the address in our memory where this actual method is stored, and we pass on that address. Just as we would pass on the address of an object that is stored on the heap, we can also pass on the address of a method in the program memory, in the protected area. And because it's marked as a delegate, the computer and the compiler specifically knows that this is not just data. This is not data we can add to something. I mean, okay, let's not go there. But it knows that this is a delegate, this is special address, this is a special reference. We can invoke this address. We cannot look at the data in there. We can decide, run the code that is at that address, at that memory location. That is a method. Pretend the A variable here refers to normal code and execute it as such, as if we jumped there, as if we called that as a normal method call. Because that's what we do in here as well. If you say A, if we do that entire spiel with preparing the stack, preparing memory in stack, reserving memory there, and passing on the control flow to there, That exact same logic is done here as well with the invoke. Actually, I can make it even more obvious. I can leave that out and just put the brackets behind. So this lowercase a is not the variable a anymore. This is referring to the method stored at the same location as b is. So if I do b up here, or if I call a up down here, exact same stuff. The same thing happens. The same code in our memory is going to be called. The only difference is up here, we hard-coded the address. We told the compiler explicitly only this one address, this specific combination where you stored b. That and nothing else. While down here we said, use the address that was provided as an argument. When we compile this, we do not know where this points to. We do not know what call we call. But at runtime, it knows this is a reference to some part in memory where code is stored. Execute that. So we can also pass on a. Well, actually, we can't pass on a because that's not... a has a parameter now, an argument. That doesn't work, but we can have c. Actually, let's do something useful in here so you can see the difference. Hey, that's b, actually. And this is c. Let's call it let's just call it method. Make it less confusing. So we can call a with b, or we can call a with c, or we can call b directly, or we can call c directly. If I run this code, yeah, wait, let me read key. Let's do read key so the console actually halts. I can see it. So first call is b, so we see b. For the second call, we passed on c, so we see c. And down here, well, one-to-one, we specifically called those methods. So that all works. That's what we can do with delegates. And we can give our delegate a special name. So right now we use a predefined delegate called action, which is limited to a void method without arguments. But we can actually define our own by using a special keyword. Pretend we're creating a field. You can make something like a public delegate, delegate, and the rest is more like a method. It's gonna be not so void. It's called method pointer to confuse people. It's not gonna have any arguments. So it looks very similar to abstract, just a different keyword. Imagine it like an abstract method, something that's not implemented but just exists for all the child classes. But we use the keyword delegate instead, so this is not an actual method of program. You cannot inherit this. You cannot override this. It's just a delegate. And now we can change this to method pointer. And that's the same. Use the keyword delegate to define a void method without arguments. And so every time we call a, we provide a method that has no return value and no arguments. So b and c fit perfectly. Let's do it more interesting. String s, that. Now method pointer requires an argument, a string argument. So b and c do not fit anymore because they don't have arguments. We need to add them. String b, let's be very creative here. String c plus b plus c that, so they spit that out. And we can do 1, 2, that. Now this one gets a bit more interesting, although actually it doesn't, because we still can just use the normal brackets and call this like the method call directly. Or we would use the invoke, method.invoke, and then provide an argument. But this way it looks a bit more direct. And when we call this now, for the first one, we got B, which is correct, with a 3, and for C, also a 3, which is correct, because it's hard-coded down here. And I just noticed I forgot the space in here. And for the direct calls, we got the values we provided in here. B got a 1, C got a 2. Okay, so that's it for delegates. There are some more interesting things you can do with them, but the basic is just methods can be packaged as an address and passed around, so you can dynamically call methods instead of providing, for example, an enum and going through a switch that determines which of those existing methods is getting called. Which is very useful for libraries, because in a library you might want to execute code provided by someone else later, so you don't even have the option of providing a switch statement with different enum values. You need to be a bit more general in that case. So let's go back here. So let's put that back to the start, but we can keep the console out. And we do the same here, CV, A, just to void methods without arguments. Let's keep the console read. So back to the thread. Creating new thread, and internally we're gonna store a delegate, like A, because again, delegate, just as we stored as an argument, we can also store it in a field, in a class or struct. Perfectly possible. As long as it's just the address, you can store it as data, because the address is data. It's just using that data works very differently for a delegate. Because using data means you run functions on them, but using delegates is you run it as a function. There's a different way to use the data, but up to that point it's just an address somewhere in memory, and you can treat it the same regardless of if it's an address on the heap for data or an address in your program space for methods. Create a new thread, which is A, and we could now just go thread.start. What we did here is prepared a class that stores a delegate to A. So this thread is now decided will start with method A. This is a new thread. This doesn't have any running code. We just defined this thread exists and it will start in this method. This is its starting point. This is its main method. Someone, well, Windows, well, actually more like the framework, doesn't matter. Someone decided to create a new thread when we called our program and put our main method in there as a starting point. That's why we start in the main method. And now we ourselves create a new thread and put an A as the starting point. This thread is independent from our current thread where the main method is running. This is important. When I call the start method, that is when I decide start processing this thread, start executing the code. Before I do this, it's all just prepared statements. It's all just create a thread, do not start it, just prepare the memory and arrange everything to be ready to be used later. When I call start, only then will it actually start running the thread and actually start processing the instructions in A. Let's do the second one. Thread A is this, thread B gets B, of course. And then we're gonna call thread A start and thread B start. And let's do this. Let's start main AB. Let's start again. Main AB main. Let's start once more. A main B. Every time I start, the order in which these appear will be more or less random. Because all of these are independent threads, our current main method is in one thread where we started at, and A and B are both running in a separate thread that we start from the main, but still in a separate thread. All of these threads get processed independently from one another. There's no synchronization between them. And we don't have any control over which thread gets processed first and for how long it gets processed. Going back to our little drawing here, imagine that this whole thing doesn't refer now to the computer as a whole, but just our own program. So this thread might be the main method, and this thread might be for A. We do not get to control which of these threads is currently actively used. If we have multiple cores in our computer, in theory, they could be run in parallel, truly parallel. More likely, however, only a single core will take care of that by alternating between them. Depends on how many resources you have and a lot of configuration that I don't even understand myself. I don't even know where to start to look into that. I mean, there are of course things like assigning threads, assigning cores to specific processes and windows, but how would I assign that? I mean, you can set priorities for different threads. We're gonna look at that soon. But generally, you don't have control over that. In the end, the computer decides on its own what it's gonna run, what it's gonna process. And A, B, and our main method all are gonna try to access the same shared resource. This is a tricky one. All of them use the console to output something. All three use console.writeLine. But they can't all write at the same time. There's a limited number of character spaces in here. If all were to write at the exact same time, then what would we write in here? Like, what is this first character gonna be? Is it an A, an M, and a B? Is it gonna look like we overlaid all letters on top of each other? Like, that doesn't make sense. For shared resources, where one process or one thread needs to have exclusive access, the other threads are just gonna wait in line. There are synchronization methods in the background. There are ways you can organize who gets access to a resource and who doesn't. And this is very, very important for multithreading. In our case, we don't have to worry about that because the console.writeLine, it already handles that in the background for us. An existing library that's already thread safe. That's the keyword you want to look for, thread safety. If we write our own libraries, we have to take care of that ourselves. Or at least if we want to have our library be thread safe. That's of course at your discretion. If you write code, it is your decision if you want it to be run or potentially be run in multiple threads, and to ensure if it's thread safe by itself or if you want to push that responsibility onto the user of your code. The important bit is only that you think about that, stay consistent with that, and communicate that to the users. If you want to write a library, you probably should mention if your classes are thread safe, so the user knows they don't have to take care of that. Or for certain situations, you preferably want to specifically mention that it's not thread safe and they have to take care of that themselves. It's just important that you know that. And in this case, it just means whoever the computer at that point decided will be the first to run is probably gonna get access first, and so in this run, it's A. A got access first, so it got to write first. And the next one was main, and then B. We started again. This one, main got access first, then B, then A. It's just basically randomness. We can sort of force an order by having these different threads start at the same time, but then wait for different amounts of time. There's a specific command that is extremely useful, but has its flaws that we need to talk about. And it is a method in the thread class. So I'm not going to add it to the main method. It's just going to run directly. A is going to get this method call before we call the console.writeLine, and it's thread.sleep. Thread.sleep is a method that will forcefully pause the entire thread. What you're doing here is tell the computer that this thread, no matter where it currently is, stop processing it and continue with other threads you have lined up. Completely ignore this thread for a certain amount of time and only go back to it once this time has run out. For a certain amount of time, do not continue with this thread. Abort it now, come back later. I shouldn't say abort, abort is different, but pause it for now, come back later. Let's go back in here. And there are two versions. One uses a more classic, more useful struct, which contains time spans, which is called timespan. It's a very useful thing. The classic one, the basic one we're using right now, is just expecting an integer value that is equivalent to the time in milliseconds we want this thread to wait. I'm going to put that at 100. That's a tenth of a second. 100 milliseconds. A millisecond is just 1,000th of a second. My God. So 100 milliseconds, that's in computer time scales, that's a lot. Like, just to mention it, 100 milliseconds is a lot of time. Pretty short for a human, for a computer, a lot. Could actually put it down to 10, that's still a lot in computer time. Just making it 100 to be sure. And we're adding a second one down here, and this one at 200. If I run this code now, these threads still get called independently. And the computer can still decide to prioritize one over the other. And it's still up to the computer if it's running threads at all. In theory, it's still possible that B is called first, for example, and only then main will appear. In theory. In practice, however, of course, your thread and the main method will not be blocked for 100 milliseconds. Again, in computer timescales, this is a lot of time, and the computer is not going to waste all that time just waiting around and not running this one thread that's just waiting. So, with this much of delay, we are definitely going to see main A, B. Actually, I'm not sure if it's visible in this stream, but you can actually see them appear one another. Maybe a bit late everywhere. Yeah, let's maybe make this a bit bigger so you can definitely see it. There we go. So this is one method, one easy direct method where we can force a certain order in threads, at least to a degree. Right now, we sleep right at the beginning of the thread. We know they're all going to start at almost the exact same time, and 100 milliseconds is a lot. The threads are not going to wait for one another that long. If I were to go down to just 1 or 2 milliseconds, then we might actually have a chance to see a different order. Main AB, let's just try it a few times. Still not enough, okay. AB, okay, that 1 millisecond is already... Okay, there we got it. Main BA. So, it took me a few tries, so you can see 1 millisecond makes a big difference already. But we can still force it with 2 milliseconds, or at least 1 millisecond in between these two. There's still just enough time to give priority to the other thread. The way we would actually want to do this is with some kind of synchronization. And the most fundamental way we can do synchronization across multiple threads is with a lock. There are more complex data structures to handle synchronization between different threads, and we're gonna look at those next time, because there's a lot today already to unpack. And they have their uses. Quite often though, I end up just using a lock, because they're easy, they're simple, they're very efficient, and they're very reliable. It's just, there are a lot of things that are a bit inconvenient if you have more complex requests. Let's make it simple. A lock is a way for your process to communicate between different threads that a certain resource is in use and you have to wait for it to be freed again. Similar to what I said earlier about dispose, where you might lock a certain file on your disk for your program and you want to free access to that file as soon as you finished. Similar style. So lock in C# always uses a specific object in the heap as the key. So we have always one specific object, one address in our heap that's filled with an actual active object. So it always has to exist somewhere, someone has to keep a reference to it. And different threads can use that one object to communicate system access. It's probably easiest if you just see it. Let me just provide a method, provide an object, static object. Oh yeah, I should mention that object is a class you can actually instantiate directly. Static object, call it lock, like that. Actually, we want to provide this with a value, and let's do that here. Lock new object. Thank you, Windows. I didn't need to know that. But thank you anyway. Actually, let's do that up here. What the hell? Not my favorite way to do it, but it works. So, pretty simple. If we do it like this, then yeah, let's keep it like that. Right now I just have a new object. Since it's just data type object itself, it's not gonna do much. It's just the bare minimum of data that is required for a valid C# object. And this is actually taking memory space on the heap. It's just taking the minimum of space on the heap that you can take for C# objects, but it's gonna fill that memory. So it's not like this is nothing. It is gonna take actual space on the heap. You can run out of space if you just fill everything with objects. But you can use any other reference type as well. As long as it's something that's sitting on the heap, you can use it for a lock. But because I don't have anything I want to use for it right now that can be reused for my locking mechanism, I created a bare minimum object that takes as little space as possible. That's a pretty common way to do it. At least in most C# language versions. The newest one actually has a special type. I think I should have it available here. Yeah, lock. So instead of an object, I would use a special type lock, which allows you to do some other stuff, but you would use it the same way. Again, it's not an object anymore. You have some special features here, but this is only in the, what is it now, C# 13, the newest version. And while it's pretty cool, and while I'm using it for every newer project, the classic way to do it would always be just having an object, if you don't have an existing object that can fulfill that role. So what I do now I'm just going to write an example code. There's a specific keyword, lock, L-O-C-K, and we follow that up with normal brackets in which we provide it with a variable that contains a reference type. So something on the heap. And for that we have our log object. And now you follow that up with a one-liner or a code block. So the basic same structure, keyword, brackets with something inside them, and then a line of instruction, single instruction, or a code block with multiple instructions, or nothing. The same basic layout we have for a lot of things in C#. This is now a log statement. Our code will go through this program step by step. The computer will go through our code step by step, each instruction by its own, until it hits this log. Once we hit this log statement, it will try to get access to the locking mechanism associated with this memory address. So it's not changing anything about your object directly. You cannot actually tell if your object is used for a lock. So if you write any data structures, like this class program, you would not be able to determine if someone uses you for a lock. It's just the address must exist, and you just use it in a different locking mechanism. It's internally using monitor. There's a special class for that you could use yourself, but you shouldn't. That's why I'm not talking about it. And it's using this just as a key. It's just, here's basically just the address, just a random number. No, pseudo random. Pseudo random. And I want to claim access to this locking. I want to claim this part in the synchronization. I want to get access. And it is associated with the address of this object. Do I have access? Yes or no? If the answer is yes, then I just continue with my code. And if the answer is no, because someone else already has gotten access, then you wait. Then you put your current thread on ice until the computer, internally it tells the computer, hey, I need access to the resource associated with this object, but it's currently locked, so my thread will not continue working until that object is freed again, until the lock is open and I can enter. So only one thread at a time will be able to enter this code block. Once you're inside this lock, you can be sure that your thread is the only thread that has access to this specific code segment across all threads that have a lock mechanism targeting that same object. So I can put my console. So this is not going to do anything, just demonstrating how one would use it. If console maybe wasn't thread safe, if console required us to make sure that we don't have different threads writing at the same time, because it would break things, I could put this inside the log statement. And I would also put these other inside log statement. And because it's a one-liner, I'm just gonna put it like this. And now I can be sure that across all threads, this console.writeLine will be only called by one thread each time, because they all have wrapped it inside a log statement, and they all use the same exact instance in the heap as a key. They all agreed we communicate through this one address. That's their communication line. They use the log statement, which is a bit centralized. Again, internally it's using monitor, which you should not do yourself. And the way they agree on what specific resource they want to target, they use an address provided through this object. And the reason we use objects is because it gives us a unique identifier, because only one object will use this address. You cannot have two different objects in the same address, so it's unique in that sense. And as long as we keep this object alive, we will always know exactly which address we're talking about. We always will talk about the exact same address because we're all targeting the same instance. It's gonna become a problem once you drop it, once you remove this object, but that's what we talked about management earlier. As long as there's a reference anywhere, and we obviously have a reference here, you cannot remove it, and that memory space will stay active and in use. So it's just a very reliable way to agree on a shared resource without us providing specific keywords ourselves. So we don't need to provide a specific number we type in ourselves here. It's just internally handled that way, very convenient. And with that, only one thread at a time will be able to enter the log statements and run the code in there. So this is not going to change anything terribly. They're still out of order. That makes sense. But at least we can be sure that all the console.write lines are running entirely on one thread only. And only once that is finished can another thread call console.write line. Now we want to talk about the synchronization a bit more. This code makes sure that only one thread can manipulate things. We want to now determine the order. We want to make sure that A cannot run until A main is finished, and B cannot run until A is finished. And there are different ways we can do this, but the simplest would be to just have integer. Let's make a static integer. Static int counter, let's put it like this. This is not a good way to do it, but it's a way to do it. We start with counter equals 0, just to be sure. I mean, it's gonna start with 0 anyway, but just so it's clear. And this is just gonna enter, write main, and then it's gonna set counter to 1. And this one is gonna first check if counter is 1. Only then do we want to output something. And when we did output something, we set counter to 2. Again, this is not a good way to do it, but it is a way to do it. If counter equals 2, correct, then we want to output B, and we can, just for clarity, set it to 3 then. So in theory, if main runs first, the counter will be set to 1. And because it's in a protected code block here, in a log statement, we know that only once this code is complete can either of these two, if they try to run, continue. And they will check first the value of counter. If it's a specific value, only then, if it's the value associated with their process, they will run their code, output something, and increase the counter so someone else can do it. The issue, of course, is if A, for example, starts first, it will enter the log part earlier, and it will execute this code safely. Main has to wait for now, even if it activates while we are inside this log statement here. But counter is not 1, so it will just do nothing and drop out. And then main will execute at some point. And B might execute at some point, but since counter was never increased to 2, it will also never do anything, and the only output we will get is main. So we have to do something unpleasant. We have to include it in a loop. We don't know how long it will take, so we're just gonna make an endless loop for now. We're just gonna repeat this, and only once this is done will we break out of the loop. And we do the same here, while true. That, and once that is done, to re-break out. Now the reason this isn't so great is because this code will just continuously repeat, go into the log statement, check if counter is advanced, go out of the log statement, repeat, go into log statement, check if the counter is advanced. If not, drop out, leave the log, repeat. For one, that means this thread is constantly running, only to check basically this one variable. And all the while it's doing that, it's gonna block this log statement. It's gonna lock this block that other threads are trying to use as well, minimizing the chance that they get access early. Because as long as it's blocking, the others cannot use it. So while you do wait, you don't want it to repeat immediately. You want it to check if you can execute, if you got lucky. But if you cannot run it directly again, do not repeat immediately. Instead, wait. Let's do 10 milliseconds, which is a lot of time. Actually, let's reduce it to 1 millisecond. Just wait a bit. And depending on your program, this might actually be a pretty large time step you want to wait. Maybe even a couple minutes or hours. For us, just 1 millisecond is good enough. Because everything is supposed to be pretty quick, and as we saw earlier, 1 millisecond is already pretty much what you need to almost ensure the order. But yeah, we don't want to immediately go back. We want to pause the thread for 1 millisecond, and that 1 millisecond is already plenty of time for the other threads to catch up and potentially increase the counter. So that's why we set it to 1 millisecond. It's a good trade-off between fast response time and pausing resources, because if we do need to constantly check this thread again, even though we are pretty much guaranteed to not have the counter set to 2, that's wasting time. Switching between different threads, switching the context to different threads to execute different parts of your program takes resources, takes time. And so you don't want to do it too often. If you can force your thread to sleep for a while, that's a better approach. Again, this is not a good way to do it, it is a way to do it. There are better ways to handle synchronization, but for that, we want to wait for next week when I show you some more advanced data structures for that. For now, with just a log and a simple case like this, perfectly fine. It's doing the job. So, let's try run this again. A after main and B after A. Let's maybe change this around. Let's change this to 2. And this to 1, 2. Let's try again. Now we get B before A. And pretty reliable. We can even do something like this. Thread sleep. Let's wait an entire second in the main method. So plenty of time for the other threads to do their thing. Still, main is going to be first. So using this log statement, we were able to organize things a bit here. Now you might be wondering, what if I don't increase or check the counter inside the log statement? That's already a bit of the problem taken care of, right? If I put the log inside, leave outside, then I don't block this code unnecessarily. Put this down, put this up. I'm not blocking this part of the code unnecessarily, so increasing the chance that the other processes might catch up. And technically, in our case at least, that is fine. This code, I can run it. It gives us the expected outcome. Everything is okay. There's a source of danger here though. Counter might be increased in one thread, or one change to 1 in this thread, while at the same time checking its content in this, or maybe at the same time also this thread. Counter is one address in memory. It's static, that's the whole point. So it's the same memory space that all 3 threads are targeting. And I'm changing the value of that memory address in the exact same moment, potentially, that these other 2 threads are changing it. Checking it, at least. For us, that is not too big of an issue right now, because we're talking about an integer, which is one of the so-called atomic data types. They are small enough that the computer can change the value of that memory space instantly. So the same moment we change it, it is filled. There's an old value and there's a new value. It goes in one operation. Not every data type is atomic. Most data types aren't. If we talk about reference types, for example, things get iffy. And with structs, we are definitely not atomic anymore. Usually, you want to make sure that changing a value and reading it happens in distinct time slots. You don't want to have something writing the value while something else is accessing the same memory space. It's no problem if different threads try to read at the same time. No conflicts there. They're all targeting the exact same point in memory, and they're all just extracting from there. But as soon as at least one thread changes anything, you want it to be the only thread. The issue you might have is when... Actually, let's quickly draw that out. If you have a certain memory cell and you're changing it, you're not necessarily changing it all in one go. Memory is actually pretty large, with many different bits inside, and the operation that fills it might take a couple of clock cycles to fill it completely. Atomic data types like int, as I said, perfectly fine, it will fill it up in one go, one operation, and it's either the old value or the new value, no conflict here. But if you have a larger data type, or at least one that's not specifically intended to be atomic, you might actually fill just one part of the value, then someone else reads the data with partially the old one and partially the new ones, new bits, and gets a mixed value that's neither the old nor the new one, a completely corrupted value. And now the operation continues with its second step, where it has to fill in the next piece of data. And only now it's one complete value for the new data set. That's only one of the possible issues you have if multiple threads target the same memory space, but it's a very important one that I think sometimes gets overlooked. Int is safe, just like Boolean would be safe. Basically all the basic data structures are pretty much safe, but you can look that up specifically. I'm not too sure about something like... No, I would look that up. If you're not sure, look that up, but I'd say the fundamental data types, int, long, actually long might be, but int, character, bool, those are fine, float. Instant one operation, immediately set no corrupt data. If you have a reference, if you have a struct, something larger, you might actually get a corrupt value. So that's an issue. That's why this is not the safest. We can do it for us right now, but this is the safer option, because no matter what type of data counter is, we always can be sure that only one thread is accessing its memory region. As long as you keep it the same everywhere, of course. So, at safety, general rule of thumb, if you access a part of the memory inside a log statement once, you should always access it from a log statement everywhere else. So as soon as you have one log statement where you change the value, you probably want it to be accessed in log statements everywhere else as well. Exceptions occur, of course, depends on your intentions. Sometimes it's a variable that doesn't need to be logged and it's just used in the context of another log. Perfectly understandable, fine. Just case like this, make sure it's all synchronized and safely stored in a single log statement that only one thread can access. Okay, I think this is a good drop-off point for today. This is giving you the basics. So next time we talk about some more issues you have with threading, because suddenly you have to think in parallel of all the different things that can occur because your code is not a singular thread anymore. We go from A to B to C and then maybe split off into two different parts. We have A and B occurring at the same time and all the different timing issues and a lot of things that are not intuitive directly. And of course, are going to have a look at different data structures that make synchronizing stuff a lot easier. And that can potentially make code like this also more efficient. Yeah, all of that next time. Thank you for joining in. No homework, no worries. Bye bye.